Today we're going to talk about compound events, section 11.4. So in continuing on with our probability, now we're going to talk about a little bit more advanced probability. So what happens now when we have compound events? Okay. For a lot of the problems today, we're going to talk about a deck of cards. Is everybody familiar with a deck of cards? Because we had a lot of people in the first hour that are like, I've never played cards before. So I know, right? It's a shame. But as long as you're familiar with deck of cards, you can be just fine today. Just have that memory. A couple things here first before we get started. Vocabulary. A simple event. A simple event is an event that cannot be broken down any further. For example, rolling like a 3 on a number cube is a simple event. Okay, it's just your basic probabilities. Those are simple events. A compound event is an event made up of two or more simple events. For example, rolling a 6 on a number cube is a simple event. Rolling an even number is a compound event because there's multiple things going on there. Okay? And then we have what's called mutually exclusive events. Mutually exclusive events are events that cannot occur at the same time. Tossing heads and tossing tails are mutually exclusive events. They cannot happen on the same toss of a coin. Rolling a 1 or rolling a 2. You can't roll a 1 and a 2, right? They're mutually exclusive events. Okay, so there's kind of the difference there. Addition rule for the probability of mutually exclusive events. A and B are mutually exclusive events. So if you want to find the probability of this or that happening, you need to, what this is showing is you need to add your probabilities. For example, a card is drawn from the deck. What's the probability of drawing a 5 or a face card from the deck? Okay, so what happens here is you look at, well, what's the probability of drawing a 5? Well, 4 out of 52 or 1/13. What's the probability of drawing a face card? Well, that's 12 out of 52 or 3/13. So what's the probability of drawing a 5 or a face card? Well, I add the probabilities and you end up with 4/13. Okay, so probability of mutually exclusive events is you're finding each event and then you're going to add them. So it's like this or this happening. Somebody earlier asked a great question. It's like, well, that's the difference between like and ors. Correct. Okay, the ors are where you add them. The ands earlier, like we did yesterday, we're going to multiply them. The probability of getting this and this. Okay. So let's look at a problem here. Tony draws a card from a deck. Find each probability. She draws a number card or a king. So first of all, what's the probability of drawing a number card? How many number cards are there? There are 40 out of 52. Or that simplifies to 10/13. What's the probability of drawing a king? How many kings are there?
4.
So 4 out of 52. Or that's 1/13. Now, what's the probability of drawing a number card or a king? I would add them and end up with 11/13. Okay, so that's mutually exclusive events. Can't happen at the same time. Number 2, she draws an ace or a queen. Well, what's the probability of drawing an ace? How many aces are there, Jack? 4? 52? Or 1/13? What about a queen? What's the probability of grabbing a queen, Mark?
4.
What?
4/52.
4 out of 52. Which is 1/13. So what's the probability of grabbing an ace or a queen? It would be 2/13. Because you'd add the two probabilities. Okay, so feeling good about that? Those are your mutually exclusive events. Those are kind of the easier of the two we're talking about today. Because the other one we're talking about is what's called inclusive events. Inclusive events are compound events that can occur at the same time. So they can occur at the same time. Basically, they're like overlapping events. So, for example, rolling a 6 and rolling an even number. Why do those overlap? Because the 6 is an even number. So, for example, rolling a 6 and rolling an even number on a number cube are inclusive events because 6 is an even number. Because inclusive events can happen simultaneously, you do not want to double count the probability when the events overlap. Okay, so you don't want to double count those probabilities. So the difference here is now we need to subtract the probabilities. So for example, The addition rule for the probability of inclusive events. A and B are inclusive events. So you find the probability of A, find the probability of B, and then you need to subtract those overlapping events. So the A and B, those are what we call the overlapping events. Okay, so for example here, it says a card is drawn from the deck. What's the probability of drawing a 3 or a heart from the deck? Well, let's start here. What's the probability of drawing a 3? 4 out of 52. What's the probability of drawing a heart? 13 out of 52. Now, what's the probability of drawing a 3 and a heart? How many 3 of hearts are there? 1. So there's one event that overlaps. So I add the first two, and then I subtract that overlapping event to find my exact probability. And that's the inclusive event. Okay? Now, does everybody know why we have to subtract it? Well, technically, I have a 3 of hearts here. And technically, I have a 3 of hearts here. I'm counting it twice. But how many 3 of hearts do I actually have in the deck? Just 1. So I'm going to subtract that 1 off, giving me my true probability. That's why I have to subtract it out. Okay, because I'm double counting it. So what they overlap, I have to subtract it out, so it's only counted once. Big key on these problems. So let's look at number 3. Charles draws a card from a deck. Find each probability. He draws a red card or a king. Well, how many red cards are in the deck? Half the deck, so that is there are 26 52 red cards. Because if they're not red, they're black, right? How many kings are there? What's the probability of grabbing a king? 1/13 or 4 out of 52? I'm gonna keep it with the big one right now, just because it's gonna make it easier at the end. Okay, how many red kings are there? 2. So I'm going to add the first 2 probabilities, and then I'm going to subtract the overlapping probabilities. So 26 plus 4 gets me 30, minus 2 is, I get 28 out of 52, which simplifies to 7/13. So the probability of getting a red or a king is 7/13. Okay. Let's try number 4. He draws a diamond or a face card. What's the probability of grabbing that diamond, Mr. Monahan? How many diamonds are there? Anybody, how many diamonds are there? 13? There's 13 of each suit. So I get 13 out of 52. And then it says probability of grabbing a face card. Well, how many face cards are there? 12 out of 52. And then it says I have to subtract the diamond face cards. How many diamond face cards are there? 3. Because Jack, Queen, King, right? There's 3 diamonds. So I'm going to add the first 2 probabilities and then subtract the overlapping probability. 13 plus 12 is 25 minus 3 is, so I end up with 22 out of 52, which simplifies to 11 out of 26. And again, the key is there you have to subtract those overlapping events. Okay, you can't add it in there twice. All right, good work. Take a couple seconds, try these 5. Okay, the first 3 are your basic exclusive events. The first 3 are the exclusive events. The last 2 are the inclusive events. Okay, so take a couple seconds, try these 5. So number 5, Pam rolls a 3 or a 6. What's the probability of Pam rolling a 3 or a 6? What do you say, Mr. Melody? Mr. Melody? It is 1/3. Nice job, sir. Because it would be 2 6 because you have the 3 or the 6, 2 6 or 1/3. Nice job. Number 6, Pam rolls an even number. What's the probability of that happening, Mark? Yep, just a half. That's just your basic probability right there. Number 7, Pam rolls an odd or even number. Crazy answer here because the probability is 1. Yeah, no matter how many times you roll that thing, you will every time get an odd or an even number, right? That's a certain event. All right, number 8, Pam rolls an odd number or a 3. What's the probability of rolling an odd number or a 3, Mr. Stefaniak? What? It is not 1/3. It is actually, what'd you say? It's 1/2. Because the key here is what's the probability of rolling an odd number? 3 out of 6. What's the probability of rolling a 3? 1/6. How many 3 odd numbers are there? 1/6. So you add the first, subtract the second one. Those basically cancel out, giving you a 3/6 or 1/2. Number 9. Pam rolls an odd number or a number greater than 4. Well, what's the probability of getting an odd number here? That's the answer. What's the probability of getting an odd number first, though? 3/6. What's the probability of getting a number greater than 4? Now, how many numbers greater than 4 are odd numbers? 1/6. So you add the first, subtract the second there, and you end up with 4/6 or 2/3 as your inclusive events.
0.
Wow.
No way, I said.
So nice job there. Try these two on your own. Same idea, dealing with some probabilities. Take a couple seconds to try these two. These are in 1/3 of the bags. What's the probability of randomly choosing a lunch bag that contains either an apple or a banana? What's the probability of grabbing one or the other of those, Maddie? 7/12. Nice job. And then number 11. A group of senior citizens have won free vacation packages. The vacation to Bermuda is chosen by 25% of them. 60% choose Alaska and 15% choose Costa Rica. What's the probability that one randomly selected senior citizen chooses to vacation in Costa Rica or Bermuda? What do you say, Mr. Heiss? How many are in Bermuda? How many choose Bermuda? How many choose Costa Rica? And what are you going to do? And you get 40%, which is 2/5 as a fraction. Nice job. Okay, last thing we're going to talk about today is we can use Venn diagrams to actually help this as well. Now, Venn diagram is just one of those ways you can use to interpret math. This might be important for, like, I don't know, ACT. I don't know, do you guys have any Venn diagrams in the ACT at all? I know for sure probably the NISA test might have a Venn diagram. Okay. So it is kind of important to recognize for all you juniors out there getting ready. But here's what it says. It says, of the 65 students going on the soccer trip, 43 are players and 12 are left-handed. Only 5 of the left-handed students are soccer players. What is the probability that one of the students on the trip is a soccer player or is left-handed? So it's the same thing as this mutually inclusive event. Okay, now the first thing we want to do is we want to start with the middle bubble here. Okay, so how many are shared? No, how many are shared? How many are players oriented left-handed? There are 5, right? Now, if you notice, we have 43 players and 12 left-handed. So this bubble right here has to represent how many? 43, right? So what does that outside bubble have to have then? 38. Right? Because 38 plus 5 would give me to 43. Same on the right side. How many does this bubble have to represent? 12. So I have 5 on the inside, which means the outside has to be 7. Now you can distinctly see all the different people, right? Am I counting people twice in this now? No. So to find the probability when you're using a Venn diagram, you can just strictly add here. So 38 plus 5 plus 7 gets me how many people are either left-handed or are players. What do you get then? I think you get 50. 50 out of 65. You get 50 out of 65. Right? 50 out of 65. Which simplifies to then 10/13.
What's your question? I just started adding.
What's the probability of getting a soccer player or left-handed. Okay. Now again, what we were doing earlier was we were like, well, you could say 43 out of 65 plus 12 out of 65, and then minus the overlapping events, 5 out of 65. And if you do that, you'd still get the same answer. Okay, this is just showing you can use it on a Venn diagram, cut it all up, and you don't have to write it all out. Okay, so there are multiple ways to represent this. All right, take a couple seconds, try number 13. It says, of the 220 people who came into the Italian deli on Friday, 104 bought pizza and 82 used a credit card. Half of the people who bought pizza used a credit card. Big key right there. What's the probability that customer bought pizza or used a credit card? Again, take a couple seconds and try this. All right, so let's try number 13. First off, how many people bought pizza and used a credit card? How many people used both? 52. And again, how do we get that? Because the key was right there. Half of the people who bought pizza used a credit card, so we cut that in half. Well, I know 104 bought pizza. 82 used a credit card. So how many people just bought pizza and paid cash? 52. Well, how many people used a credit card and didn't buy pizza? So they used a credit card and bought a sandwich. 30. Exactly, right? Come on. So then what's the probability of grabbing or selecting a customer that bought a pizza or used a credit card? It would be what? 134 over 220, which simplifies to, what did you say? 67 over 110. Nice job. And again, that's kind of comes from that visualization there. Now you can distinctly see all the different people in there. All right, good work. Here's your assignment.